Welcome back. This is the fourth lecture on numerical methods for conservation laws. And in this lecture, which consists of two parts, we talk about the concept of entropy solution. Let's recap the necessary context. Previously, we have seen that weak solutions are natural for conservation laws because classical solutions are too restrictive to work with in practice. So we need weak solutions, but it turns out there's no unique weak solution in general. For example, we've seen multiple possible weak solutions for Berg's equation, all starting with the same initial data, but taking vastly different forms. So consequently, we would like to develop criteria to single out the correct or physical weak solution. Among the class of weak solutions, we want to find a particular weak solution that we deem physical or correct. Entropy conditions will help us to identify those. So we have got multiple weak solutions. How do we pick the one that's physical, if there is any physical one? One selection criterion has already been mentioned last time. Generally speaking, we want the characteristics to run into the shock curves, but never to emerge from the shock curve. This is illustrated in the diagram below, which reminds us of our last example in discussing Berg's equation. For example, in the rarefaction wave, no characteristic ever emerges from a shock wave. All characteristics emerge from the initial data. No information is ever created at the shocks. Information can only vanish into the shock curves. Okay, that is the selection criterion by which we are going to work. Let's put this into a more mathematical form. Recall, if the flux is differentiable, then the conservation law can be written as time derivative of u plus f prime of u times x derivative of u equals 0. Now, along a shock curve with speed s, the characteristics shall run into the shock. Consequently, characteristics from the left must be at least as fast as the shock speed, and characteristics from the right must be at most as slow as the shock speed. When we say fast and slow in this context, then fast always means towards plus infinity, and slow always means towards minus infinity. Mathematically, this means that the lax entropy condition holds. F prime UL is greater equal S, which is greater equal F prime UR. Here we recall that F prime UL is just the speed of the characteristics that transport the value UL, and F prime UR is the speed of the characteristics that transport the value UR. This selection criterion, the lax entropy condition, emerges fairly naturally from our requirement that no characteristics ever emerge at a shock. Let's have a look at two examples. In the two diagrams below, you see characteristics transporting some value on the left and characteristics transporting some value on the right. And you see a shock curve in between. In both examples, the characteristic speed on the left is larger than the shock speed, which in turn is larger than the characteristic speed on the right. In the example on the left characteristics are fairly fast, whereas the characteristics on the right have speed close to 0, and the shock speed is somewhere in between. In the right picture, the characteristics on the left have speed close to 0, and the characteristics on the right have a negative speed. And the shock curve, again, has a speed somewhere in between.
We demonstrate the utility of the lax entropy condition with two simple examples. First, we take a look at the transport equation with constant speed. Here we have that f prime of u equals a for any choice of u. Consequently, any discontinuity must move with the speed a, just the transport speed of the system. In particular, the weak solutions that we have derived previously for the transport equation are now recognized as satisfying the lax entropy condition. Our second example is Burger's equation. We have f prime of u equal 2 times u, and that has got a consequence for the shocks that satisfy the Lax entropy condition. The Lax entropy condition requires that UL is greater equal UR. So based on the Lax entropy condition, all the discontinuities that arise in Burger's equation must satisfy that the value to the left is larger than or equal to the value on the right. So based on Lax entropy condition, we can already filter out a certain class of shocks as non-physical.
We can also identify one more entropy condition. The argument for that is due to Lou. Suppose we start again with discontinuous initial data. The initial data have some constant value UL and then jumps to another constant value UR. UL might be smaller than UR, or UL might be larger than UR. Now, in both cases, suppose we perturb the initial data by an intermediate state that is illustrated below, where in between we introduce an intermediate state U star, just by shifting the initial discontinuity a little bit. And U star, of course, is taken from somewhere in between UL and UR. Intuitively, the small perturbation at the start should not amplify over time, because we never have got exact measurements for its initial data. So we can only hope that the physical system is stable under small perturbations of the initial data. So if we suppose that small perturbations at the initial data do not amplify over time, what are the mathematical consequences? Well, one must be that the jump behind travels not slower than the jump ahead. That can be expressed, of course, in terms of the RH condition, since the RH condition always computes the shock speed. We have that FU star minus FUL divided by U star minus UL must be greater equal FUR minus FU star divided by UR minus U star. This is known as Lou's entropy condition. And Lou's condition means that a shock is only physically admissible if the states UL and UR satisfies the condition above for any choice of intermediate state U star. In other words, the shock must be stable under perturbations. Lou's entropy condition can be visualized in terms of function graphs. So we consider the flux function f and how it depends on u in the two drawings below. The green solid line depicts the graph of f as we draw it over the values of u in between ul and ur, and the dashed orange lines represent points on the graph that we connect. To the left, we have the situation that ul is less than ur, and to the right, we have the situation that ur is less than ul. In both cases, we draw a second line that cuts the graph of the flux function f at the points ul, ful, and ur, fur. And we also draw the secants, and we also draw the secant lines that pass through u star, fu star, and the other 2 points, ul, ful, and ur, fur. Lou's entropy condition basically states that the slope of the secant line passing through ul, ful, and u star, fu star must be larger than the slope of the secant line passing through u star, fu star, and ur, fur for any choice of value u star in between ul and ur. But that means when ul is less than ur, then f must actually stay above or on the secant line between ul, ful, and ur, fur. And when ul is greater than ur, then the opposite is true. The graph of f must stay below the secant line. That is illustrated in the 2 graphics below. So Lou's entropy condition for scalar conservation laws has got a very nice graphical illustration. Lou's entropy condition that the shocks are physically stable, that the intermediate shocks have a speed faster than the original shock, can also be expressed directly as follows, namely using the RH condition. It must be that fu star minus ful divided by U star minus UL is greater equal FUR minus FUL divided by UR minus UL. Again, that can be expressed graphically below. Up to now, we've seen some concrete entropy conditions for scalar conservation laws in one dimension. Those entropy conditions have helped us to filter out unphysical solutions. That certainly is progress towards our goal of finding the unique physical solution among all the different weak solutions of conservation laws. To complete that agenda, we now study conservation laws and entropy conditions from a slightly more general point of view. That is the second part of this lecture. In the second part of this lecture, we will develop the notion of entropy solution. In particular, the correct weak solutions are so-called entropy solutions. That theory is set up now in several stages. First, we introduce entropy pairs. Then we introduce the notion of weak entropy solution using the notion of entropy pair. Number 3, we show that weak entropy solutions typically are the vanishing viscosity limits of conservation laws. Then fourth, we study the contraction property of entropy solutions, which will show us the uniqueness. In fact, we show that entropy solutions actually exist for all conservation laws. And finally, we study some additional properties of entropy solutions. So let's take a look at the notion of entropy pairs. We say that two differentiable functions, eta from the real numbers into themselves and psi from the real numbers into themselves, are an entropy-entropy flux pair, eta psi, compatible with the flux F if first the entropy function eta is convex, and second, the following identity holds: eta prime of u times f prime of u equals psi prime of u for all possible real numbers u. That is the definition of entropy-entropy flux pair. And in fact, we can immediately generalize this a little bit. Whereas here we have taken derivatives of the entropy, the flux, and the entropy flux psi, we actually do not need to assume that eta, psi, or f are differentiable. We only need to assume that this equation holds in the sense of distributions, to be explained later. We also note that entropy and entropy flux pairs always depend on the flux. So if we use the notion of entropy pair, entropy flux, this is always to be understood together with some flux function f that we have in the back of our minds. Let's take a look at a few examples for entropy and entropy flux functions. Now, one example is very simple. You take eta u equal u and psi equal f. We easily check that this is an entropy-entropy flux pair. In particular, the notion of entropy-entropy flux pair is not completely empty. There is at least one example. In fact, there are infinitely many examples. Given any convex differentiable function eta, which shall be our entropy function, we can construct an entropy flux psi of u as follows. Namely, we define psi of u equal the integral from z naught up to u of eta prime z times f prime z dz. Here, z naught is any arbitrary choice of left integral boundary. And with that definition, eta psi will be an entropy-entropy flux pair compatible with the flux f. Let me emphasize that the choice of z naught is completely arbitrary here. Varying the choice of z naught will only change psi by addition of a constant. But as we shall see, this constant never matters in calculations. Finally, we consider the Kruskov entropy-entropy flux pair. Here, eta of u equals the absolute value of u minus k, where k is some arbitrary value, and psi of u equals the sine of u minus k times f of u minus fk. Here, k is again an arbitrary choice. The Khrushchev entropy-entropy flux pairs are quite important, but they are not differentiable functions. This is why we have introduced this slightly generalized notion of entropy-entropy flux pair. However, it turns out that convex functions can be approximated by linear combinations of such entropy functions, such Khrushchev entropy functions, eta. Okay, so we verified that there is a rich selection of possible entropy-entropy flux pairs compatible with any given flux F. Now we can define entropy solutions. Suppose that U is an integrable weak solution to the conservation law with a continuous flux F, and suppose that we have got integrable initial data that are also essentially bounded. Then we use the following definition. We call U a weak entropy solution if for all entropy pairs eta psi, the following inequalities are satisfied. The integral from 0 to infinity in time of the integral over the real line in x of eta of u times time derivative phi plus psi of u times x derivative phi dx dt plus the integral over the real line in x of eta u naught times phi dx is greater or equal to 0 for all non-negative test functions phi. So again, we may think of phi as some bubble that at some point emerges locally and then vanishes again. If that inequality is satisfied for all such non-negative test functions phi, then U is called a weak entropy solution. Please notice that this inequality must also be satisfied for all possible entropy-entropy flux pairs. Please notice that we can simplify the setting also when U is a classical solution. In that setting, in that situation, eta of U can be conceived as a conserved quantity. To see this, we observe first that 0 equals eta prime of U times t derivative of U plus x derivative of f of U. That first inequality is true because now we assume U to be a classical solution satisfying the conservation law in the classical sense. Now that equals eta prime of U times t derivative of U plus eta prime of U times f prime of U times x derivative of U. Now we recognize an application of the chain rule. The first term can be replaced by t derivative of eta of U, and using the definition of entropy-entropy flux pair, the second term can be replaced by psi prime of U times x derivative of U. And in the last step, the second term can be further simplified to x derivative of psi of U. So we have that 0 equals t derivative of eta of U plus x derivative of psi of U. And to connect this with the notion of weak entropy solution, all remains to be done, not shown here, is to multiply this with any arbitrary non-negative test functions and perform integration by parts. The notion of weak entropy solution can also be interpreted as follows. When U is a weak entropy solution, then the definition of weak entropy solutions implies that the entropy is non-increasing in a distributional sense, that is, eta prime t derivative of eta of U plus x derivative of psi of U is less than or equal to 0. And that is just another way of writing down the definition of weak entropy solutions, but in the sense of distributions. And that is why we call eta the entropy associated with the function U.
Now, why is this notion of weak entropy solution a physically relevant, a good notion of solution? At first, it looks fairly abstract. However, we can relate it to the vanishing viscosity limit that we've encountered earlier in the discussion of Berger's equation. We recall that Berger's equation could be seen as a limit of a second-order partial differential equation with a second-order viscosity term. As the viscosity term goes to zero, as the viscosity vanishes, Berger's equation emerges, at least informally, as a limit. As it turns out, we can relate the notion of vanishing viscosity solution to our notion of entropy solution. In order to appreciate that connection, let us suppose we have got a smooth solution u epsilon x and t to the viscous equation time derivative of u epsilon plus x derivative of f u epsilon equal epsilon times Laplacian of u epsilon. Here epsilon is a small parameter close to zero. We have initial data u epsilon x 0 equal u naught of x. And this new partial differential equation can be interpreted as a modification of our conservation law, where we now have introduced this viscosity term, epsilon times Laplacian u epsilon on the right-hand side. Conversely, as epsilon goes to zero, we recover our conservation law. Now suppose that u epsilon is uniformly bounded for all epsilon in between 0 and 1. In particular, as epsilon goes to 0, the solutions u epsilon all satisfy uniform bounds. Now, if u epsilon converges to some bounded function u, almost everywhere, then the limit u is a weak entropy solution. Let's reassert the physical relevance of that observation. Previously, we have argued somewhat informally that conservation laws can be derived as a vanishing viscosity limit of viscous equations. So it seems reasonable that the limit of the solutions to those viscous equations, as the viscous term epsilon vanishes, should converge to the physically correct solution of the conservation law. And this theorem tells us that this limit, as epsilon goes to 0, is in fact an entropy solution. That's a very strong hint that entropy solutions are the correct physical solutions to the conservation law.
Let's get on with the proof. Here I follow Evans' book on partial differential equations, in particular chapter 11.4.2. First, suppose that eta and psi are smooth functions. Since by assumption, the time derivative of u epsilon plus the x derivative of f u epsilon equals epsilon times second x derivative u epsilon, we can multiply both sides of the equation by eta prime of u. And then we get, using the definition of entropy flux pairs, and of course the chain rule, the following identity: time derivative of eta u epsilon plus x derivative of psi u epsilon equal eta times epsilon times eta prime u epsilon times second x derivative of u epsilon. Let's take a closer look at the term on the right-hand side. We observe the following: epsilon times eta prime u epsilon times second x derivative of u epsilon equals epsilon times second x derivative of the entropy eta u epsilon minus epsilon times eta prime prime u epsilon del x u epsilon times del x u epsilon. This is just an application of the product rule. But now, since eta is a convex function, we must have that eta prime prime is greater or equal to 0. Consequently, eta prime prime u epsilon times del x u epsilon times del x u epsilon is greater or equal to 0. Because we multiply this non-negative term eta prime prime with a square. So that term certainly is greater or equal to 0. That term will be important in establishing the inequality in the notion of weak entropy solution. Now we pick any non-negative test function phi with compact support. in R times the positive real numbers. Now we multiply the entropy conservation law by phi, then we integrate and integrate by parts. Thus we arrive at the following observation. The time integral from 0 to infinity of the x integral over the real line of eta u epsilon times time derivative of phi plus psi u epsilon times x derivative of phi dx dt equals the integral from 0 to infinity in t of the integral over the real line in x of eta epsilon eta prime prime u epsilon times x derivative of u epsilon times x derivative of u epsilon times phi minus epsilon eta u epsilon times phi xx times second x derivative of phi dx dt. Now we use the inequality from the previous slide and the fact that phi is non-negative. So we arrive at the same left-hand side as before is greater equal negative integral from 0 to infinity in t of the integral over the real line in x of epsilon eta u epsilon times second x derivative of phi dx dt. Now we recall that u epsilon is uniformly bounded and that eta and psi are smooth functions by assumption. Now as epsilon goes to 0, we can use the theorem of dominated convergence and arrive at this desired inequality. The integral from 0 to infinity in t of the integral over the real line in x of eta of u times the time derivative of phi plus psi of u times the x derivative of phi dx dt is greater or equal to 0. And lastly, if eta and psi are not smooth, then we can use smooth approximations and take the limit. And that finishes the proof. This indicates that the weak entropy solutions are actually the correct solutions, since many conservation laws arise via the vanishing viscosity simplification. In this theorem, we have supposed that the almost everywhere convergence was already given. Now, in practice, establishing the almost everywhere convergence of u epsilon towards some function u is a major challenge in using the vanishing viscosity approach. So we should see this as, first and foremost, a theoretical result that corroborates our intuition that entropy solutions are the correct solutions.
Apparently, entropy solutions have interesting connections to vanishing viscosity limits. That already is a big hint that entropy solutions are the correct notion of solution. There's also another interesting property, the so-called contraction property, which will eventually establish that entropy solutions are unique. That can be seen as follows. The key result here is due to Kruskov and was proven first in 1970. Kruskov's theorem reads as follows. Suppose that u0 and v0 are essentially bounded functions, which will serve as initial data, and suppose that u and v are the respective weak entropy solutions to the conservation laws with the corresponding initial data u0 and v0. U and v are essentially bounded in space and time, and we also assume that u and v define a continuous function from the time variable t into the space of integrable functions. Now, u and v are assumed to be solutions to the same conservation law with the same flux function, del tu plus del x f of u equals 0, and del t v plus del x f of v equals 0, with the respective initial data ux0 equal u0x and vx0 equal v0x. Under this assumption, del t of the L1 distance of u of t and v of t is less than equal 0. This theorem can also be summarized as follows. if you've got two solutions to the same conservation law, but with possibly different initial data, U0 and V0, then the L1 distance between the two solutions, U and V, does not increase over time. It can only decrease. So practically, if I've got two solutions to the same conservation law, but with different initial data, then over time, the two solutions will not diverge apart from each other, but they might converge to each other over time. As already mentioned, the contraction property, in fact, implies the uniqueness of the weak entropy solution. The application is quite simple. Suppose that U and V are two respective weak entropy solutions to the same conservation law, delta U plus delta XF of U equals 0, with the same initial data, Ux0 equal U0x and Vx0 equal U0x. To show uniqueness of the solution, what we need to show now is that U equal V, is to show that U and V are the same, U equal V. The important thing here is that these two solutions, U and V, satisfy the same initial condition. Now, according to the theorem on the previous slide, the L1 distance of the two solutions over time does not increase. It may stay constant or it may decrease. But at t equals 0, let's take a look. The L1 distance of U0 and V0, that's just the L1 distance of U0 and, well, U0. Obviously, that equals 0. So we have that the L1 distance of the two solutions starts at 0 at the initial time, and it cannot increase over time. So consequently, the L1 distance must stay 0 for all times. And in particular, that means for all times t greater or equal 0, we have that U of t equals V of t. In other words, U equal V, that is, the two weak entropy solutions are the same. And that is, weak entropy solutions are unique. So far, we've not discussed the existence of weak entropy solutions. We've seen some interesting properties, and we've seen that weak entropy solutions are unique. It is a separate result to show that weak entropy solutions actually exist. The existence of weak entropy solutions is another result proven by Kruskov in 1970. We state it in the following form. Suppose that U0 is an essentially bounded function. It's a bounded measurable function. And suppose that the flux, for simplicity, is twice differentiable. Then the scalar conservation law as a unique weak entropy solution U, which is essentially bounded in space and time, and which defines a continuous function from t into the space of locally integrable functions.
Lastly, we discuss properties of entropy solutions that are particularly relevant in the discussion of numerical methods later on. Here we refer to a paper by Conway and Smoller from 1966. So let us suppose that U0 is an essentially bounded function which serves for our initial values, and that we have got a weak entropy solution U, which is essentially bounded over space-time and which defines a continuous function in the time variable mapping into the locally integrable functions. Conway and Smoller have proven two interesting properties of such weak entropy solutions. First, if U0 is in the space of bounded variation functions, if the initial data have got bounded variation, then the same is also true for the weak entropy solution U at all times t. Now you might ask, what's BV in this context? Well, BV is the abbreviation for bounded variation, and that will be discussed on the next slide. Furthermore, if U0 is monotonely decreasing or increasing, then the same is also true for the entropy solution U. In that sense, monotonicity is preserved. Now, what about the bounded variation? What about the BB space? To make sense of that, we need to introduce a new term, namely the total variation. The total variation of a function, how much the function graph moves. Specifically, before we take a look at the proper definition of total variation, let's first have a look at a few examples. If u is a function from the real numbers into themselves that is differentiable, then the total variation TV of u is defined as the integral of the absolute value of the derivative of u. More generally, if u is a continuous function, then the total variation of u is defined as follows. We consider all partitions of the real line by nodal points. So we take all increasing sequences of nodal points along the real line, and for each such sequence, xi, xi plus 1, and so on, we take a look at the sum over all the indices I of the absolute value of f of xi plus 1 minus f of xi. For all such partitions of the real line, we take a look at the corresponding sum, and then we just take the largest one. More precisely, we take the supremum of those. Interestingly, total variation is also defined for functions that are not continuous. If u is a piecewise smooth function with countably many jumps at nodal points xi, xi plus 1, etc., then the total variation of u equals the following expression. On the one hand, we sum up the integrals of the absolute value of u in between the nodal points. That's the first term here in the first equation. And then we add the absolute values of the jumps of the function u at the nodal values xi. That formula for the total variation of u is particularly appealing because apparently it is also defined for functions that we've seen earlier in our discussion of conservation laws. After all, we have seen that the solution of conservation laws may be piecewise smooth with a few jumps in between. And for such functions, we can define the total variation. Now, those are all just examples. Technically, we can define the total variation of any function u as follows. Provided that u is a locally integrable function, the total variation of u equals the supremum of all the integrals of u against derivatives of test functions phi, where phi is a C1 function, compactly supported, and has a maximum norm bounded by 1. Now, the very last definition of TV is actually the proper definition of the total variation, but for most applications that we encounter, this will be a little bit too unhandy. In most cases, our function u will have enough structure so that a simpler definition for the total variation can be used in those special cases. And now, finally, we can define the space BV of functions with bounded variation. That is a set of integrable functions u for which the total variation is bounded. That's very simple. And in fact, that space can also be equipped with a norm. The bounded variation norm of a function u is defined as the L1 norm of a function u plus its total variation. And for those of you who like function analysis, the bounded variation space equipped with that norm is a Banach space. Without going into too much detail, functions in the space of bounded variation can have quite strange forms. For example, the Cantor function. The Cantor function is a piecewise constant, monotonely increasing function with countably many jumps having non-zero total variation. So in this case here, all the increase of this monotonely increasing function stems from the presence of jumps. In fact, infinitely many jumps. And as you can tell, some of those jumps actually accumulate at certain points. That function is just to illustrate that bounded variation functions can look quite strange, and it is used, in fact, for many counterexamples in real analysis. So what's the whole point of bounded variation in the context of conservation laws? Now, on the one hand, the space of bounded variation is large enough to contain, for example, piecewise smooth functions. In particular, it is large enough to contain functions that we encounter in our discussion of how to solve conservation laws. For piecewise smooth functions, possibly with jumps, we can easily compute the total variation. As we've seen before, we just take a look how large are the jumps and integrate the absolute value of the derivatives in between. In particular, for many of the proposed solutions, we can already compute the total variation. And then we've seen that in many cases, when solving a conservation law, the solution actually is in the space of bounded variation at all times. In particular, the variation of a solution does not blow up in finite time. That, for example, means that the sum of the jumps does not explode arbitrarily. Likewise, we do not expect the gradients to become too large. So it seems that bounded variation is a very useful notion for our discussion of conservation laws.
This has been quite a collection of results. For that reason, let us review a few important publications in the literature on the theory of conservation laws. The notion of entropy solution was first introduced by Orleinik in a publication on discontinuous solutions of nonlinear differential equations that covered scalar conservation laws in one space dimension, and subsequently Kruskov discussed scalar conservation laws in higher dimensions. On the other hand, the situation for systems of conservation laws still has many opportunities for development. In this context, I only refer to a recent survey by Bianchini and Bresan from 2005, addressing systems in only one dimension. And that already is quite some hardcore analysis, I must say. The solution theory for systems of conservation laws in higher dimensions is still a largely unexplored field, and not many general results are available in the literature. Some of the results I've used in this presentation can be found also in the literature. There's a publication by Serré and Silvestre on multidimensional Burgers equation, from which I've taken a few hints. We also refer to another publication by Bresan on hyperbolic conservation laws. I've used some items from Evans' textbook on partial differential equations. And last but not least, I would like to mention the following quote by Todd Moore, which further illustrates the situation for systems of conservation laws in one or higher dimensions. Let me quote: "The basic questions regarding entropy solutions for general systems are still open. Instead, the present trend seems to concentrate on special systems with additional properties which enable to answer the questions of existence, stability, and large-time behavior, etc." I think this quote nicely sums up the situation in the literature. For scalar conservation laws, most of the major results have been settled, but for systems, in particular in higher dimensions, there is still lots of work to be done. We close this lecture with a short summary. So what we've seen is that classical solutions are too restrictive for applications. That is why we've introduced weak solutions. Those are good, but they are too broad already. There are infinitely many weak solutions in general, and for that reason, we need to single out entropy solutions, which are the weak solutions that are physical. First, we've introduced various selection criteria, for example, the Lax entropy condition or Lewis entropy condition, in order to single out non-physical shocks. Then we've introduced the definition of entropy and entropy flux pairs, which in turn led to the notion of weak entropy solution. We've seen that the limits of the vanishing viscosity solutions are entropy solutions. That's a strong hint that entropy solutions are actually the physical solutions. We have discovered the L1 contraction property of entropy solutions, which has implied also the uniqueness of entropy solutions. We have briefly discussed the existence of weak entropy solutions for conservation laws. And then one major point has been bounded variation. So much for now. Until next time.